All right, welcome back. We'll continue with our development of the finite dimensional weak form. What we had got to doing at the end of the last segment was using the bi-unit domain to not only write out our basis functions, but also to set up the integrals that go into the weak form. Okay? So we'd written out the integrals that go into the weak form, into the finite dimensional weak form for the general element by using this approach, and that's where we're going to pick up today. Right. So the topic of the segment that we're going to work through today is the matrix vector weak form. And in order to get to it, essentially I'm going to continue where we were last time. Okay, recall that we'd written out the form of the following integrals for the case of the general element. Okay, we'd written out this integral wh comma x sigma h a dx for the general element. Okay, and it's in your notes, it's in the slides corresponding to the last segment. What I'm going to start out with doing is consider this integral for the somewhat special case of element 1, fueled by the fact that we have a Dirichlet boundary condition on the first node of element 1. Okay, so we have this, and now let's consider how it works out for E equals 1. Okay, now for element E equals 1, this is the integral over omega E. wh comma x, you recall, for element 1 is written as simply n2 comma c comma x multiplying c to e, where e for this particular case is 1. Okay, so this is our expression of wh comma x. All right, it multiplies EA, and then we have our contribution for the gradient of the trial solution, and that takes on the form sum over B NB comma C comma x dBE, and this is our representation of UH comma x. All right, integrated over dx. All right, and now of course we take our approach of going to the bi-unit domain in order to write out this integral. From that we get integral over omega c. The first term is, the first factor here is n2 comma c. We have c comma x. Okay, and we recall that c comma x is simply 2 over he. Okay, and here we have c2 e, ea here, and for UH comma x we have NB comma C. Again we get C comma x. We use 2 over HE for that as well. We have here DBE. And now like we did in the previous segment, we're going to rewrite dx as dx we are going to write as dc dx sorry, it is dx dc dc. All right. Now dx dc we know is he over 2 dc. All right. And as we did in the segment last time, those cancel out. Right. A similar sort of exercise for the next integral, integral over omega e wh f a dx leads to, after going through these sorts of steps, we get integral over omega c. Our representation of wh here is simply n2 times c2e, and remember this is all for e equals 1, which is why we don't have the contribution from the first basis function, right? We talked about that in the last segment. This multiplying f a, and now in place of dx, once again we have dx dc, right? Let me write that as dx dc dc, and we recall that this is he divided by 2. Okay, so we have these two integrals also written out for the special case of the very first element, and you recall that what this does is to leave out the use of the first basis function, right? These integrals here involve only n2. Okay. All right. So we have this in place, and what we are going to do now is essentially look at how all of these terms contribute, how all of these simplifications or these expansions contribute to setting together the weak form. Okay. So now, in order to do that, let's consider the general case. Consider for a general element omega e. Okay, and let's consider this the first of these integrals, the integral that comes from the left hand side of the weak form. Okay. That integral is integral, now we now have it written as integral over omega c sum over a n a comma c. Let me write this as c a e a sum over b n b comma c d b e, and the term that survives here after cancellations of d x dc and dc dx type of factors is this one. Okay, and we have here dc. All right, now this needs to be simplified, and the way we can carry out the simplification is through several steps. The first of these steps involves us recognizing that the c's and the d's that are used here are degrees of freedom, right? The c is the degree of freedom that is used to interpolate the weighting function. The d, b sub e, is the degree of freedom that's used to interpolate the trial solution, right? So what we do is to recognize that these degrees of freedom are independent, right? They're independent of the variable of integration, right? They're independent of xi, right? Because these are the actual degrees of freedom that are being interpolated by basis functions that are being expressed in terms of xi. As a result, we can pull them out of the integral, okay? So that allows us to write this out as follows. We can now pull the summation symbol out, and for the sake of brevity, I'm going to write this as a sum over a and b. Okay? We get c, a, e outside the integral, and within the integral we have the integral is over omega c. Okay? We have here NA, comma C, EA, NB, comma C. I'm going to pull the factor of 2, which comes here. For the sake of brevity, again, I'm going to put it in here and divide by HE. Okay? So I have that factor 2EA over HE sitting inside there. All of this is integrated over dxc, and that is our integral, okay, within those parentheses, and it is being multiplied by dBE. Okay, written nice in a nice and short, succinct form. All right. We have this for this integral, and let's do the same thing for the integral that involves the forcing function. Okay, that integral is integral over omega c sum over a NA C A E F A, and we get here HE over 2 dxc. All right. Again, observing that this is independent of xi. Therefore, it can be pulled out of the integration. We get sum over a C A E integral over omega c N A F A, and once again I'm going to put the HE here, in this case divided by 2 dxc. All right, this is what we have. And now observe that in the case of the first element, right, it's going to look very much like this, except that the sum over A will not be required, right, because A will take on only the value 2. Okay, so let me just recall this. For E equals 1, there is no sum over A. Instead we have we require to use just the index A equals 2. Okay. And why is it that we need to use the index only A equals 2? It's because the first basis function is not used in element 1, recognizing the fact that we have a Dirichlet boundary condition on element 1, and therefore the weighting function contribution from the degree of freedom 1 is not used. Okay? So instead we use A equals 2, because we know that WH at 0 has to be equal to 0, okay, implying that WH in that element, right, for E equals 1, WH is only written as N2 C2 E. Okay, all right. So we have this, and we're now going to go ahead and construct from this a form of the weak form that we call the matrix vector form. And in order to do that, we need to look at that expression and that one. The first step to getting to a matrix vector form of the weak form is to attempt or is to aim to eliminate these sums. Okay, and the way we will eliminate those sums is by writing them out using matrix vector products.